is my pleasure to introduce our next speaker, Dr. Annika Vogt. She will give a talk on the next generation drug delivery system, which parameters are shaped with improved penetration in hair follicles.
Thank you for giving me the opportunity to speak. And we are changing a little bit the perspective, because people who know our group know that, and we've certainly heard and seen a lot of interesting molecules over the past talks, and I'm not interested in trying to bring the old and the new to the spot where they're supposed to act and keep them there. And we also, I will show you in a minute how we also try to create basic understanding of skin barrier physiology through that. One second. So the overall concept that particulate forms of particles or particle encapsulations tend to preferentially aggregate in hair follicle organs, that's pretty old. This has been demonstrated nicely for acne pores. They are dilatated, so if you have a microsphere, you can put them in there, and it's also been used and marketed in several products these days. Also, we personally were involved in previous studies where we looked at particulate forms of anti-dandruff shampoos, where the deposition of the shampoo could be correlated to the activity and presence of Malassezia species. But this is all superficial. This is like putting something in and having it there. And also there's been various works over the years trying to figure out, can we use those particles for something else? And what about size? Nanotechnology, do we need it or not? And there's lots of literature out on people who try to identify the perfect size of a particle to bring it perfectly down a big hair follicle or a small hair follicle that is sometimes being confused by people who are not so familiar with hair like us. And in our own work, when we started to work with biodegradable polymers, we also found that despite the fact that technologists can nicely produce particles in aqueous solution, it's critical to see what they really do on the skin surface, because this we know from the micellar type, liposome type vesicle particles, that when they come in contact with the stratum corneum, they interact with the lipids and really sort of shuttle compounds across these superficial layers, but then they are gone, they don't get deeper, which has advantages and disadvantages. And by looking at how we could load such polylactic acid particles with either more different ranges of lipophilic drugs, basically, we could see that the load also determined the stabilization in the hair follicle and the kinetics by which the compounds were released. And I also kept wondering, what do we do with a lot of the drugs we have are actually lipophilic, so how happy are we as hair people with the lipophilic drug which sits in the sebum? Is this really our goal? So now to the basic science. I will show you examples of polymer-bars particles, not because they're probably the only way of approaching questions, because this is the way we try to understand more. And now we are getting really small, and it will become clear. I have to be fast in the short time stack, so you will see. What we do see in these core multicell structures is that they have a core and then shell layers, and they are allowed to be decorated in a way to modify stability and hydrophilicity. And we do see, even though they're really small, around 5-ish nanometers, they still penetrate in hair follicles. And we need to move from the color dye research to more drug-oriented research. So we did a lot of studies. We did co-investigation of carrier material, like here, covalently labeled in green, and then questions, where does the drug go? Dexamethasone, and then pictures is one thing, and you all know how difficult quantification sometimes is, but then also we did extracts and mass spectrometry, and we found, and this is just examples from many other works, that these type of particles were able of bringing in model substances, like the dexamethasone, as example for small lipophilic easy, but also we have worked with tacrolimus as example for large, low soluble, deeper into the epithelium. And this is really, for most of us, reach technical limitations, and that's where collaborations with basic scientists become really exciting. Then through collaborations with our colleagues from the physics department at Free University, we have access to X-ray microscopy approaches, and together with them And we'll also see, I'm happy to say that this was done in collaboration with Kenji Yamamoto, a Japanese PhD student, and Professor Kozugi in Okazaki University. We are now able to detect label-free drug penetration profiles. So you minimize artificial staining, handling, and so on. And with the X-ray microscopy, the resolution is so detailed that you can here identify molecules and carriers depending on their chemical properties within stratum corneum, and you can localize it and you can calculate absolute concentrations in relation to depth. So this will help us, as the example with cream, dexamethasone for 16 hours in the carrier that you see in the cream has the reservoir, as we all know in dermatology, in the stratum corneum, but the CMS for some reason brings it deeper. So we have less reservoir and deeper areas. And then the chemists can even do more, and in clinics we don't really take much advantage of that at the moment. So one other thing also based on these polyglycerol constructs is that we work with stimuli-responsive nanogels. And I will quickly, just to demonstrate that we did some work basically on penetration generally, but the interesting feature is that they have transition temperatures and they change their properties. So when you warm them up, this is illustrated here, and that's the other thing, you can measure this with atomic microscopy and these quantification nanomechanics. So when they get warmer, they harden and stiffen and they squeeze out their load. It's especially good for large molecules. For example, they did work with biologics, etanercept, and they could load it onto it. And with these techniques, we were able to follow cryosem here intact nanogels in stratum corneum, and we also try to correlate the different states with penetration and cellular uptake behavior. It's kind of nice. You apply it on the skin, it's rather elastic, that promotes penetration across the stratum corneum, but then inside it gets harder and it squeezes the drug out and also changes cellular uptake likelihood. We could show with TEM microscopy that the hydration state of the stratum corneum is altered. And with Raman spectrum microscopy, we could study the lipid-protein ratios. This is really just spotlights, but what it illustrates is that we now have tools, and we don't use it that much yet, to not only monitor drugs or say, I see an image and now it's in the hair follicle, but we can try to correlate it back to chemical properties and to biochemical environment to learn about skin barrier. Because at the moment, a lot what we do when we try to formulate and when companies come and say, oh, you're good in drug delivery, how would we apply it? It's a lot observational. You have one compound, one goal, and one assay, but we don't have comprehensive information really to make good predictions, because at the end, what we all want as an MD, and I'm also treating patients, so I see that problem every time where you have to convince people applying their drug every day, daily, for years, and they have business. So when we want to decide which one do we want to produce in GMP grade and put into trials, we need to understand better, and we hope that with these tools we can understand this, and we are lucky to have a collaboration now with mathematicians who put all our experimental data in model programs and will help us make prediction. Like based on these absolute concentrations with the diffusivity and free energy profiles, they are able to detect barriers that at this point we haven't even known. And after all, this is, again, these single papers, and that's why I showed so many spotlights, are sometimes hard to read. They are technical and frequently published in basic science papers, but the end is really our goal to, and we can use those tools to make these compounds available. We've had talks about siRNA. I mean, this is not future anymore. We have those compounds. We have successfully worked on peptides, and so we are very positive that if we just are able to manage this big data, that we come up with better concepts than we have right now, and that as derm people we can learn more of hair follicles. And lastly, I was very excited to see a poster by Wonsu Lee's collaboration, I think, on lipid barriers in the hair follicle, the truth is we don't really know much about which pathways our compounds really take and how do they get to the dermatopilla where we want to get it. And so this is my experimental research unit. Here at Charité we have the advantage in our study center that we have a clinical trial unit and these research capacities. And this partnering with basic science partners as we do this in this national funding program on nanocarrier and nanotechnology for clinical applications, I think will be really helpful to generate more information. Thank you very much.
Thank you for your very important thoughts. And are there any questions?
Later because it's clearly a lot of different little puzzle pieces.
Okay, thank you. And we will continue, and our next speaker